So, good morning, everybody. It's now time to start this session on users and applications dedicated to demanding applications. And my name is Lígia Ribeiro from the University of Porto and also from UNIS. I will be sharing this session. And in this session, we will have two speakers, not three, because Federico Grasso was not able to come here. So the other speakers, Paul and Stefan, will share the time. They will speak for about 40 minutes with 5 minutes for questions. So we are going to hear about two applications in different areas, but they both demand high-speed networking. And the first application is in the radio astronomy area. So we will have Paul Boeven that is going to speak about eVLBI. Paul is a Linux and network specialist work in GIVA, the Joint Institute for VLBI in Europe. So, Paul, the floor is yours. Thank you.
Okay, so where's my presentation come? Yes.
And just desktop.
5C?
No. Just
Close that one.
That's it. Demanding
5C,
applications.
yeah, okay.
And you should find it right there. That's it.
Okay, thank you. Welcome everybody. My name is Paul Boeven. I work at JIVE. JIVE is the Joint Institute for VLBI in Europe, as Ivan just told us. And that's a lot of acronyms, which I'll start going through first. What is JIVE? JIVE operates the EVN correlator. The EVN then is the European VLBI network. That's the same acronym again. And we are at this moment running the Express project. Express is a project to develop eVLBI and bring it into a production stage. And at the moment, our goal is to have a real-time eVLBI network consisting of many continents and up to 16 radio telescopes. So a little bit about radio astronomy. There's basically dishes. They receive the signal. It gets focused into a receiver. We record it for later processing. So with radio telescopes, you look at different things than with optical telescopes. Whereas with optical telescopes, you see very hot things like stars. With radio telescopes, we mostly see gases. So we look at completely different things in the universe. But there is a slight problem with radio telescopes. If you have a single radio telescope, well, let's first look at the Hubble, which is one of the best optical telescopes. So the resolution of a telescope basically depends on two things. The aperture, how big the area of the telescope is, divided by the wavelength, and divide that over the wavelength of the observation. So the Hubble telescope has a resolution of 0.06 arc-second. So it is only a 2.4 meter mirror. Now if you look, for instance, at the Onsala Space Observatory, which is a fairly standard radio telescope, it has a 25 meter dish, so it's 10 times as big. Unfortunately, the radio observations are at a wavelength of 6 centimeters, so we end up with only 600 arc-seconds of resolution. And just to give you an idea how much that is, the moon is about half a degree. 600 arc-seconds is about a third of that. So you only have 3 pixels to view the complete moon. So that's a fairly poor resolution. So what we would really like is a dish that is 240 kilometers in size to be comparable to the Hubble, for instance. It's a bit difficult because the biggest dishes are about 100 meters, that they're fully steerable. And then there's Arecibo, which is built into a natural valley on Puerto Rico, which is 300 meters. But of course, you can't steer that, so it can really only look straight up and a little bit around that. Fortunately, there has been a solution for this, which was developed especially in the UK at first. It's called a very long baseline interferometry. The idea is that you have not just a single dish, but that you have a lot of radio telescopes, and you create a virtual radio telescope, and then the resolution really becomes as if you had a radio telescope that is the size of the biggest distance between these dishes. The sensitivity is of course much less than when you had a real dish that was 240 kilometers. So you only have, at several locations within this area, you have some dishes, but still the more dishes you have and also the more bandwidth you have, the higher your sensitivity gets. Because all these radio telescopes are on their own locations, they're all independent, you need a very accurate time. Come in on these huge tapes, single reel tapes. Not your ordinary backup tape, because these tapes in 1990 could do up to a gigabit per second recording and playback. But they were fairly fragile, we couldn't really reliably get a gigabit out of it. So the EVLBI community then changed over to disk packs. And this is packed with 8 hard disks. And we sent a lot of hard disks around the world to all the radio telescopes. They record on these hard disks and they send it back to us for processing. For instance, this month we sent out about half a petabyte worth of hard disks in the mail. And there's currently recordings going on, and once those are all finished, all those disk packs go back to Jive, will be correlated. This is still very cumbersome. There's huge delays in getting them because all radio telescopes are really in out-of-the-way places. We like radio telescopes that are far away because the bigger the distance, the better the resolution we get. So if you have to wait for a disk pack, for instance, from Chile or something, that can take weeks. So we've started with the development of real-time EVLBI, where all the data basically comes in on the fiber. The yellow one is our 10 gigabit connection to SurfNet. The orange ones are our 1 gigabit light paths, and then we have the 10 gig internal connections as well. And the switch has grown a little bit since this picture. We now have 16 10 gig connections to our playback units. So a little comparison once again. For instance, the station in Chile sent out about 2 terabyte twice a week, so 4 terabyte a week. So on average, that would be only 61 megabit per second. And this graph is from somewhere in 2007, early 2007, and then we were able to get comparable speeds on the network, where we could get 58 megabit per second. Of course, the huge difference is that here the latency is 2 weeks, and over there the latency is only 150 milliseconds. And Andy Tenenbaum once famously said, never underestimate the bandwidth of a station wagon full with tapes hurtling down the highway. That is still true. We still do a lot of disk-based VLBI because of the sheer amount of data. But the network is really catching up in speed, and we're doing now about more than a quarter of our VLBI is now done on real-time fibers. So why do we do this eVLBI and not just regular VLBI? The quick turnaround is one of them. But also we can respond very rapidly to new things that happen in the universe. It used to be that a VLBI observation had to be planned months in advance. We had to see if we had enough disk space for the particular observation. We had to send the disks to the observatories that were involved in this observation. And then months later you would get the disks back. Now, if something new happens, for instance, a supernova in a nearby galaxy or a flare of a binary star, we are able to schedule this on a day's notice if really necessary. So we've suddenly created a completely new class of radio astronomy where we can now, with the highest possible resolution, look at things that previously we knew were happening, but we couldn't take a close look because we simply didn't have enough disks. It's also very important that we can check things as they happen. Because this is a fairly complicated game. There are radio telescopes and they have down converters. We have to sample it. We have to convert the data to the network. All of these steps, or record the data on disk, there are many things that can go wrong. And it's very beneficial that we can just look at the data as it comes in real time and see if we get the right data from these telescopes. Of course, we also get rid of a very huge headache in logistics. where hard disk packs would become delayed. We would receive deleted or damaged ones or destroyed ones. Lately, we've had a few cases where we are trying to play back a hard disk pack, and then some chip on the hard disk actually catches fire. It's also very interesting. So you've sent the disk pack to the United States or wherever. They've done the recording. You get it back. You try and play it back, and then all of a sudden you have a power outage because we have a very advanced fire detection system to safeguard our correlator. And at the very first hint of smoke, it will cut the power, cut all the electrical power. So suddenly you are in the dark, and well, actually the lights stay on, but the rest of the correlator goes dark, and all the other systems. And we've now had this 3 times, and the last time we actually caught it just in time, so one of our operators was actually spotted running outside of the building, holding a disk pack that was smoking just to make sure that the fire alarm would not go off, because not only does it go dark, within a few minutes we also have the fire department visiting us. This is all because the correlator that we have is a fairly unique instrument built from special purpose ASICs, integrated circuits that were just developed for this task, and is really irreplaceable in that sense. So here's another example. This is a flare-up of Cygnus X3, which is a binary system. It irregularly flares, and this was an attempt on the left to watch such a flare with regular VLBI. Unfortunately, we completely missed it. And this was the first time we did it in eVLBI, and we managed to observe it. And so what you see here in this red square is actually this area, and this is the eruption that is happening and that's being studied by the astronomers. Now this year, as you might know, is the International Year of Astronomy. We had a bit of a introduction to that at the last Terrena, where we're very glad to be the keynote speaker for the final plenary. In January then we had the official opening of the International Year of Astronomy. And this is the observation we did. And what you see here is basically the throughput for all the telescopes that were in this observation. So you can see some of the telescopes are 1 gigabit data. For instance here, Westerbork, and in green, Onsala. Other telescopes only contribute at 512 megabit, some even at less. Of course, if it's less, then the sensitivity goes down, but it can still be very worthwhile because some of these baselines like Tigo in Chile or Hobart in Tasmania, all the way down in Australia, those are really long baselines, so they really help increase the resolution of the image. So this is an observation we did. And as the Earth turns and the telescopes come in different orientation in comparison to the source that we're observing, you will see actually how the quality of the image increases. You see the noise go down, and here we have the actual image that we were trying to get. So this brings us to a bit of an overview of the characteristics of VLBI. We're talking about high bandwidth, over a gigabit per second, although some of the stations have less capacity at the moment. Long distances worldwide, possibly even longer. Occasionally there are actually radio telescopes that are being launched into space, and we also do VLBI with those. We've already done that. And in 2013 there will be another launch of a system called VSOP2. That's being prepared. That's probably not going to be real time, so it's not eVLBI, but for the baseline, it's a very nice and long baseline. We do this in real time, which poses some extra hurdles, especially because our original system was based on a batch playback of magnetic tapes, so we've bolted on quite a lot of hacks and improvements to be able to do this in real time. Because we would like to have all the possible configurations from the telescopes compared to the source, and the Earth turns in 24 hours, it's best if you can observe up to 12 hours, because then we have all the possible baselines in all the possible orientation, and we get the best image. And there's also some good news. We can actually accept a little bit of packet loss. In fact, back when we were using tapes, we had bit error rates up to 10⁻⁴ on really bad tapes, and we can still, the correlation gets worse. We lose some sensitivity, but we can still correlate the data. So when we started the eVLBI project, we were doing basic network research, and of course, we first of all tried it with TCP, and within Europe, that worked fairly well. However, if you're going to places like China, and unfortunately we have to go the long way to China, as I'll show in a further sheet, you can have round trip times up to 375 milliseconds. So that's really over a third of a second. Now the way TCP works is that it starts at a very low speed, and then very carefully, every time that it notes that all the packets came through unharmed, that no packets were lost, it will increase its speed. This works fine on a local area network where the round trip time is very short. But if you have to wait a third of a second before you do the next increase, it can really take minutes. The time scale here is in seconds on the top graph. So you can see at the start you see the regular Reno startup, and then we go into TCP BIG for the people who are familiar with TCP's flavors. And you can see it stays steady for a while, and then it carefully goes up. But it goes up very slowly. And as soon as we hit any packet loss, and all the little squares over there indicate packet loss, or sorry, all the little stars and pluses are basically selective acknowledgements that tell us, hey, you missed a few packets. And you see that the rate goes down very much. And this is a 622 megabit fiber, or light pod, I should say. We're trying to do 512 megabit over it. We never even get at 300. And especially the average rate, because we want to do this for a few hours, not just reach that 300 or reach 500. We want to keep doing this for hours. So TCP is really not suitable. Then we've done really all kinds of tuning where you look at the window size, where you look at STCP, Hydra, many different kinds of TCP. But the more you tune your TCP, the less fair you become compared to the other users. Basically, we came to the conclusion that we might as well do away with the whole TCP and just blast UDP packets, because we also do not need the reliable delivery that TCP guarantees. So if we occasionally lose a packet, that's not a big deal. And over here is the same experiment done with UDP. So we do a nice 512 megabit. You can see there's a little bit of packet loss. You can see it both in the throughput and in the little crosses at the bottom. But we get the full data rate through it. Unfortunately, the first time we did this, we actually were within 15 minutes noticed by the Chinese networking people, and we had our own personal entry in the big Chinese firewall. Despite this being completely cleared with everyone, with all the NRANs in place, we still ended up being blocked, but this was fairly quickly resolved. So anyway, if we're going to use UDP, we're going to have to use private connections, because we're not going to be very nice citizens on the network. We're just going to try and blast our data through. There'll be no congestion control. So we try to use light pods or dedicated VLANs or dark fiber where possible. Now light pods, I assume that most people here are familiar with those. Light pods, when I started this job, I was a little bit surprised. A light pod is not actually something that your light goes through. It is just a time slot on a wavelength, and it gets cross-connected at different SDH equipment around the world, and it's basically circuit switched, and it is as if you had the old telephone system where you call to an operator and connects you to the next operator, the next, and the next. So they have to be built in advance. The nice thing is you have guaranteed bandwidth, you have a very stable latency. The bad thing is, especially for these long international light pods, is they tend to be a string of connected single point of failures. And this graph shows about a week, I think, in March, where we're doing an observation. And every little blip here is where we have a little outage. And as you can see, some of the outages are a bit longer. And the black squares are where we had actual observations. So over here, we were very glad to miss this one, but I'm not sure if it's actually visible there. There's here an outage, and an outage over here, an outage over here. So even during observations, these things happen. And especially the longer light paths. This is about half a year worth of SNMP traps that tell us when a light path goes down. So the top two are actually our dark fiber connections to the Dutch radio telescope in Westerbork, which has very little outages. But for instance, if you look at Sheshan, which is near Shanghai in China, if you look at the ATCA, which is the Australian Telescope Compact Array, we have quite a lot of outages on those lines. And then for the European ones, Cambridge, Jodrell in the UK, of course, the number of outages is much less. Fortunately, there's a lot of planned maintenance, and fortunately, all the NRANs are generally very good about informing us about the ongoing maintenance. Some of them are even so good that they tell us about all their maintenance, and we then have to filter out which maintenance applies to our light pods. That's a bit of a puzzle always. We always try and tell beforehand when we plan to do observations. Some of these are planned months in advance, but we are more and more becoming a target of opportunity instrument, because that's one of the strengths of EVLBI, that we can do this at short notice. So NRENs have outages that they can't plan. We have observations that are really planned very short in advance. So there's always a risk of losing one or more telescopes. It does happen. And we're trying to work with the NRENs to get the highest reliability out of this. So this is a little table that shows all of the telescopes we've been doing EVLBI with recently. The country codes to give you an idea where they are. LP stands for a light pod, R stands for a routed connection. So sometimes we have a choice of both. And as you can see, some of the round trip times over there, so it's basically ordered in round trip time, where the closest is Westerbork at less than a millisecond, and the furthest are over a third of a second away from us. Well, I'm not going to go through this whole slide with you, of course, but some things to note is, for instance, from Effelsberg, we have a 10 gigabit connection, which we share with the LOFAR radio astronomy project. And at the top, Shanghai, Sheshan, we have both a route over Tyne 2 and over a light path, and I'll show you in this slide. For instance, Sheshan is there to the right in China. Normally we use the light path, which goes down to Hong Kong, then across the Pacific, then through Canary networks, and then hops through Netherlight and Surfnet. It goes to Jive over there to the correlator and the network equipment. The other route we can use is the other way around through the Tyne 2 network. So that really depends on congestion, planning, all those kinds of things. This is Tigo. In Chile, we use the Red Clara network. Arecibo is using some VLAN path, actually. And from Australia, we used to have 3 1 gigabit light paths. At the moment, it's down to 1 gigabit. Let's see, and there's even a few telescopes in there that are still not connected. For instance, Urumqi is a radio telescope that we use regularly for normal disk-based VLBI, but it's very hard to get a connection there. We had one for a month for the opening of the International Year of Astronomy for that demo, but it was impossible to keep that connection because of the cost. And Noto over there at Italy is on a little island and is also still not connected. So we still do a lot of disk-based VLBI also for that reason, because we simply have more telescopes that way. So our network setup is extremely simple. We have light paths from radio telescopes, and we have one routed connection which we are allowed to use up to 5 gigabit. All of that goes into a switch router, and we have our own IP space, and then we have our own servers at the other end. There is a router in between so that we can apply access list, because otherwise this would simply become the world's largest backdoor network, connecting all these telescopes directly to one another. The other reason we have a router is a more interesting problem we ran into. Imagine you are doing EVLBI at 512 megabit per second to a particular receiving server. We call these Mark V servers at the right hand. So each of these servers is receiving the stream from one telescope. Now one of these machines crashes, it happens. When it crashes and you reboot it, the network interface goes down. Now the network switch sees the network port go down, and it looks in his MAC table and says, okay, I have to remove this entry because this port is down. So apparently this MAC address no longer lives on that port. The radio telescope, which is over a third of a second away sometimes, is still happily sending the data. There is no entry anymore in the MAC table, so the switch has only one option, which is to flood the traffic to try and figure out which switchboard it belongs to. As you can imagine, if you're doing 512 megabit of regular traffic and you get another 512 megabit of flooded traffic, you're trying to put 1024 megabit into a 1 gigabit port. It does not fit. What happens next is, you can guess, lots of packet loss, more servers that are crashing. That really didn't work out as well. So we ended up putting each and every server in its own private little piece of IP space. So each server is in a /30 IP space connected directly to the router, so that even if a server goes down, we're not being troubled with flooding. It's a bit of a hack, but it served us really well. I've already told you about the speeds we do this at 512 megabit, for instance, 1024. These are powers of 2 of 1 megahertz, or 1 megabit. So the speeds at which we do eVLBI are 128, 256, 512, and 1024. But 1024, of course, is more than 1000, so it does not actually fit in a gigabit. We really like to get this at the highest speeds possible, because the higher bandwidth we get, the better the sensitivity of the observation we're doing. One of the things we've tried is to randomly drop packets to bring it down to, say, 980 megabit. But it's fairly difficult to then still get a calibrated image, because you're not sure which packet you dropped. And the other problem is we are all the time calculating basically the correlation between 2 telescopes. And now if one telescope is dropping 5% and the other is dropping 5%, and these drops are not synchronized, then you're actually losing twice that. So you really pay the price of that, pay a big penalty in sensitivity when you do it that way. The other thing is it's actually, the data we get is not just a sampled piece of spectrum, it's actually many subbands sampled at 2 bits. So we have tried to throw away one of these subbands. Unfortunately, the hardware we have generates this data in a long 64-bit parallel word. Now imagine having your CPU build these 64 words, take out 2 bits, slide them together, pack them together, and do this continuously at the speeds of a gigabit. This kind of bit manipulation at a gigabit is very difficult to do and really takes up a lot of CPU work. So where possible, we try and get our bandwidth in different ways. And one of the ways we do is trunking, where we take not 1 gigabit line, but 2 gigabit line. Trunking has its own challenges. The standard trunking is called LACP, Link Aggregation and Control Protocol. Uses a hash of the source address or the destination address or the MAC address or whatever. And this is actually done to prevent reordering. And the whole goal is to have a particular connection between 2 PCs, always use the same member of this trunk. So you have a trunk with several members, but unfortunately, if you have only one sender and one receiver, if you use standard trunking technology, all your data will only go over one of those trunk links, so you're still stuck at 1 gigabit, and so you still are at too low a bandwidth. The solution to this we found is trunking, not doing the trunking on the switch, because most switches only support LACP kinds of trunking, but doing the trunking on the Linux side, on the sending side, where we basically have 2 network interfaces in the Mark V, in the server, and we make sure that with bonding that it's really distributed in a round-robin fashion. So a packet goes on the one interface, on the other, on the one, on the other, round-robin, back and forth. So each link carries 512 megabit of radio astronomy data, and together we can bring that, in our switch we can make 1024 out of that again. The important thing is to have 2 completely separate paths. If you cannot just build trunk after trunk after trunk, because your Linux machine does support round-robin, but all the routers and the switches in between do not. So you have to be very careful that you keep treating them as complete separate light paths, as complete separate VLANs, all the way until they reach jive. And that's, to quote the Ghostbusters, it's very important to not cross the streams. So the first experiment we did with that was from Westerbork, which is a radio telescope in the Netherlands, so it's close by. So we have a dark fiber between Westerbork over here on the left and jive at the right. It's about 34 kilometers. So what we did is we got some CWDM equipment, which is coarse or cheap wavelength division multiplexing. So there are 2 network cards in the server. There's a switch, and we've made 2 VLANs on it. So each VLAN has a color. All the colors go together in a multiplexer, go over the fiber, and then we split them up again. And now we run into a little snag, and that is the server or the switch at jive also is a switch that only does LACP kind of trunking. So actually from that switch to the server, we use 10 gigabit Ethernet on CX4 cabling, because you cannot start a trunk from that switch to that server, because we are still talking about a single UDP stream. And this is what the CWDM equipment looks like. So we have 8 wavelengths. We just use standard SFPs to plug in there. And we have one of these in Westerbork, and of course one of these in Jive as well, to split out the colors again. Another interesting feature if you're trying to do this kind of high bandwidth flows is timing. Timing becomes very important, especially, for instance, if you have a 622 gigabit light path, and you're trying to send only 512. You might think that would fit easily, but it turns out there is a few complications. The problem is the 1 gigabit interface in the server can really only send at 2 speeds. It can send data at a full gigabit, or it can send 0. There's nothing in between. So you need to pace the traffic, because so your long-term average will be 520 megabit, but your short-time average can only be 1 or 0, and you have to have a delay between the packets. If you try to do this in the regular Linux way, where you just use the Linux scheduler, the Linux kernel, and just wait between each packet, between each time slice that the kernel gives you, then with old kernels, they would run at 100 hertz, so you have 1/100 of a second. The more modern kernels run at 250 hertz, which corresponds to a time slice of 4 milliseconds. Now, in 4 milliseconds, you get about, at 1 gigabit, you get about 512 kilobytes of data. So your switch port, actually, at the bottleneck, where you go from the 1 gigabit Ethernet into the light path, which is only 622, at that particular point, there needs to be enough buffer to get one of those time slots completely in there, so it can then send it out at a lower rate on the light path. In practice, that usually isn't the case. So what we have to do, and if that isn't the case, what happens is that the buffer overruns, packets get dropped, and we have huge packet loss. So even if you compile your own kernel with the highest speed, which is 1000 hertz, you still have 1 millisecond timing, which is not good enough. So we've adapted our software to send a packet and then do a delay, send a packet and then do a delay. But we cannot delay by using the standard Linux sleep call, because the sleep will only return at the next scheduling interval, which is a millisecond late. So what we have to do is we have to generate our own delay by basically running in a very tight loop, looking, is it time for another packet, is it not, is it time for another packet, and then send it out. And if you do it this way, we get a very good timing between the packets. We also get one CPU that is really only doing one thing, waiting in a very tight loop, and you really have to look at the cooling if you do that for 12 or 24 hours. So the problem is solved, but perhaps not in an optimal way. Because we really have a real-time problem here, and it would be very nice to have a real-time kernel take care of that. Now, real-time kernels would be a bit of an issue, because it would mean building our own kernel, sending it to all the different radio telescopes. And so the real question becomes, what kind of hard-time real-time kernel do you need? What we really need is the high-resolution timers, so we can sleep for a specific amount of time. We don't really need the hard real-time, where you can interrupt your own kernel. A little bit of jitter, a little bit of delay variation is okay, but as long as the short-time average is good enough. So the good news is that now Debian Lenny, actually, in those kernels, will have this kind of sleep call, the nano sleep call, already integrated in the kernel. So we are now trying to adapt the drivers for our hardware to support Debian Lenny as well, because we're currently, most of the stations are running Debian Edge. And with Debian Lenny, we can actually sleep instead of running in this tight loop, and the CPU load on that particular core goes from 99% down to 5%. So that's really a much greener way of doing things as well. Now, in the United Kingdom, there is the Merlin network. Merlin is the multi-element radio-linked interferometer. It's 6 radio telescopes linked through microwave links that each have 128 megabit. Now, the interesting thing is these are fairly close together. And just as the long baselines are really needed to get a very accurate resolution, we also like the combination with short baselines, so we also get an overview of the large-scale structure of the objects that we're studying. You can imagine if the longest baseline really defines the smallest thing you can see, but the shortest baseline defines the biggest thing you can see. It really becomes a bit of a high-pass filter that any structure that is bigger then the comparative shortest baseline gets lost in the image, and that makes it harder to calibrate the data. So we've put some effort in getting data from those telescopes in as well. And now the central location for this is at Jodrell Bank in the UK, and there is a single Mark V that connects to several of these, up to 4 of these telescopes to send the data to Jive. Now the way we used to do it when we were using hard disks is we would record this data on a disk pack, send this disk pack to Jive, and then we would have to duplicate this disk pack 4 times, and then put those in 4 different Mark Vs to play back all these different telescopes that were each recorded on different tracks of this data. So we tried to do this in a different way, to have the network copy this data, because we want to do this in a real-time fashion. The first experiment I did was using a span or mirror port, which is really an awfully ugly hack. So basically, you configure one of the ports on your switch to completely duplicate the traffic that is going to another port. So it has the same IP address, the same MAC address, and everything. And then on the receiving server, you have to set the same IP address as on the other server. You have to set the same MAC address as on the other server. And then you can actually fool this second server into thinking that these UDP packets are for that particular server as well. So then we had 2 servers receiving this data. Well, this was really just a proof of concept because we don't really like having to completely hack apart our network for every observation. So then a colleague of mine came up with the brilliant idea of using multicast for this. Multicast UDP is really fit for this job where we want to have a data stream that's only sent from the UK to Holland once and then multiplied to up to 4 machines. So it's not just for video multicast, you can also use it for other UDP streams. And we are doing this at 512 megabit per second, which is quite a lot for multicast. So you really need to have hardware support in your switch for multicast, because otherwise it will just fall over. We also had to buy a special multicast routing license for this, because this is really just, these are all layer 2 connections, but our switch is a router in those 2 networks. So we had to get a special license to be allowed to route multicast through it. And we've given a special name to this project, which is now called Merlincast. And we can have up to 4 telescopes at the same time. So the way it works, the Jodrell Bank telescope has its own Mark V, and then we take 4 out of the other 5 telescopes. There's 2 telescopes, in case you think I can't count, there's 2 telescopes at Jodrell Bank. One is the Lovell 76 meters, 200 feet anyway. The other one is the Jodrell Bank Mark II, which is a bit smaller, but is much more accurate, and it's really used for the high frequencies. So we use one of those 2, and then we use up to 4 out of 5 of the other ones. This was quite an interesting experiment, but we ran into another problem. We really wanted 1024 megabit from a big telescope like the Lovell telescope to get a good sensitivity. So we wanted to use trunking to use it we have 2 light paths from the UK to Holland. So we could evenly distribute the Lovell telescope data over 2 links. But then we still had another 512 megabit from this Merlincast traffic from these other telescopes. And that's, okay, that still doesn't fit. Unfortunately, that other machine only has a single Ethernet card, so we can't use trunking on the other one. So there was really no room left for the other 512. So what I did is made a very small change to the bonding driver that does the round-robin distribution. So instead of sending a packet on one link and then on the other, on one link and then on the other, I've now made it so that it will send 5 packets on one link. So you get about 800 megabit on that link, and then you get about 200 megabit on the other. Instead of using just modprobe bonding to load the bonding driver, we've introduced a new parameter, which is the skew of the bonding. So now one link is running at about 800, the other is running at 200, and you still have room left over for another 512. So we really try and get the most out of the connectivity we have. And sometimes it really involves very ugly hacks. Oh yes, and we've dubbed this the elliptical robin, because it's not round robin anymore. Okay, so today we happen to be observing as well. Today another outburst of Cygnus X3, which is being studied by by astronomers, and we're really trying to look at the evolution of this, so we're doing this on several days. We had an observation on May the 23rd, we have an observation today, we have another one at July the 4th. There's telescopes from Australia joining, there's telescopes from Japan joining, several telescopes from Europe. So these are really long baselines that we're using. And this is the first epoch on the 23rd of May. So what you see is, we start with the telescopes Sheshan in China, Mopra in Australia, and Kashima in Japan. Because the source, first of all, rises in the east, just like the sun. And then as the Earth turns, more and more telescopes get to see the source. So first, these telescopes get lined up and we get the timing right. Then we look at a different source with all the telescopes to accurately align all the atomic clocks. Then we start the actual observation. As you can see, we had some problem with the Kashima data. This color here is Kashima. And then after a while, the European stations come in as well. And so we have some time where we have all the stations looking at the source. And then later on, the source actually sets in Australia and then later on in Japan and China. So you see the number of telescopes decrease again. And as I said, EVLBI today, we are doing this observation today. And I made this graph really just half an hour, even less, before this session started. This is the observation today. We're only in the part yet where it can be seen from the Far East, from Australia. So we've done the alignment of all the telescopes. And here, JBES, this one is the telescope close to Madrid, which joined the EVLBI world this year. So this is really on their second observation now. And so later today, because this is, I think, a 12-hour run, later today, the European telescopes will actually be able to look at the source that is already being observed from the other telescopes, so we get more traffic, and then once again it will go down. It'll basically look similar to the graph I just showed before, but this is really almost live what we're doing today. And after today, there's the future. Our sensitivity increases basically by the square root of the bandwidth. So we have 4 times more bandwidth, we have twice the sensitivity. Our current correlator is limited to 1024 megabit per station, and we're really starting to feel that now. We are researching different kind of correlators to do all this post-processing, to do all this real-time processing. We are looking at software correlators, especially for very specific jobs. But to do this on a regular cluster really takes a very big cluster. We're also researching how to do this on GPUs. And a project we've recently started is to do this on FPGAs, to make reconfigurable astronomical computing hardware that's really targeted to the kind of streaming we do, where we have a continuous stream of data that needs to go through a number of steps, Fourier transforms, multiplications, filtering, all those things that can really be done very nicely in modern FPGAs. And we are aiming at, if possible, 64 gigabit per telescope. And the other thing is, the correlator is at one end of the link. At the other end of the link, there is a telescope. So at the telescope, we need new receivers, new samplers. All these things are being developed at this moment. There's really a lot of change in the world of VLBI and EVLBI especially, that's really being driven by the new computing power, the new networks. We would also like to be able to do more than 16 stations, which is the current limit of our correlator. What you do is you calculate when you have, say, 3 telescopes, you calculate this correlation, this correlation, and this correlation. So actually, the number of baselines you see goes up almost as the square of the number of stations. So our goal for the next one is up to 32 stations, so that doesn't just double the complexity, but also makes the machine 4 times as much. So the machine also has to do 4 times as much work. Well, there used to be another slide here. Sorry. Yeah, well, never mind.
The last one.
Yeah, well, no,
No problem.
it skips it for some reason. Anyway, all it had was a pretty picture of our data center and questions.
Yes. One question there.
I have one question about TCP. You said that using TCP with a little bit of losses causes you problems. That's why you're using now UDP. What do you think about applications when we cannot have little losses? We will be limited by the bandwidth or by TCP? Do you think?
The problem is not that we cannot tolerate any packet loss. Actually, a little bit of packet loss is okay. The problem is the way that TCP responds to packet loss. If a packet gets lost, you have to do the whole congestion, you get into the whole congestion control regime of TCP, where only very slowly it increases the bandwidth again. On a local area network, that really doesn't matter because it can very quickly probe bandwidth and get the data and get an acknowledgement back that all the data came back true, unharmed, so it can try a higher and higher bandwidth really within milliseconds. But because we are talking about light paths that have a delay of 1/3 of a second, so you really can only increase it 3 times per second. So the growth rate, which is very steep on the local area network, becomes very shallow on a long distance path. And that's where TCP really starts hurting us. It's not so much the packet loss, but the throughput really goes all the way down, and you have to start all over again. And the problem is you're still generating the data at the same speed. So you get a huge backlog, and at some point your TCP just gives up.
Of course, I was speaking about long FTTs because for other applications, maybe we have long FTTs, for example, for satellite applications. And in this case, you cannot use TCP according to your experience. Like what I understand from what you have said. That if you have a very big value of LTT, so the bottleneck today is not the bandwidth, but TCP itself.
Yes.
Okay, thank you.
Another question here? Here. In front.
You gain a lot of data from different points in the LBI system. So the problem is to synchronize the all data. My question is, what kind of tools, advanced tools, you use to synchronize the process?
Well, the synchronization is really done at the telescope, where all the data is time-stamped by a clock signal from an atomic clock. So each telescope has its own atomic clock. So these are very accurate, very stable clocks. And we just send them over the network with these timestamps, and they arrive at Jive, and then we just delay all the different stations until all the clocks match up. So there's a little bit of buffering happening at the receiving end for up to 1/3 of a second, and after that, once we have all the data, we simply, for that particular second, we just put it all together into the correlator at the same time. And there's a second step to that. Atomic clocks are very accurate and stable, but even they are not accurate and stable enough for what we do. So at the start of a session, which I showed you, where I said aligning the clocks, where we look at the source with all the telescopes, we look at a known, very bright, very compact source, and we look at all the different delays, and we can actually calibrate out the errors of the different atomic clocks at the start of the observation, so that we know all these offsets, and we introduce that into the model we have of all the delays, and then we start looking at the actual source we are interested in.
Thank you very much, Paul. Let's thank Paul again for this interesting presentation. Now let's move on to another area that also needs high performance networking. We'll have a presentation on the management of large-scale video networks from the Emergence Technology Director of Polycom, Steven. I'm sorry, I cannot pronounce your last name.
That's very easy, Karapetkov.
Karapetkov. Okay, Steven, the floor is yours.
Hello, hello, can you hear me? Hello, hello, hello? It's good, okay, okay, excellent. Good afternoon, everybody. I just need to turn on my slides. Is that the slides? Ah, here we go. Here we go. Thanks for the introduction, and thanks for the organizers of this conference for inviting me to speak about video. I am Emerging Technologies Director at Polycom, and my job is really to promote our technologies to the outside world, and our technologies are mainly in the area of audio and video communication. It's a very interesting job, by the way, because right now our industry is experiencing tremendous growth. We're seeing video coming out of the video conference room and becoming available on desktop applications. We see telepresence applications. We see video deployed in all sorts of vertical applications in education, in healthcare, in government applications. And I find myself at a lot of industry events talking about the basics around video. And every time I do that, I get a lot of interesting feedback. People are very excited about video. People know relatively little about video itself. So I try to structure the presentation in a way that is really applicable to When I joined the TNC meeting in Bruges last year, I talked to a couple of people, and this is pretty much what I heard. And my question is always, what are you doing with video? And this is what I heard. I heard that a lot of universities are deploying room-based telepresence video systems. Some of them are older video conferencing systems. Some of them are low-quality video conferencing systems. Lecture rooms and auditoriums so that students from remote locations in Germany, they're using video to connect multiple campuses because they have consolidated campuses and they have half of their students in one town and the other half in a different town that is 50 miles away. So obviously they need some kind of a communication link between the two, otherwise you'll end up busing people back and forth between the two locations. Installations of large immersive telepresence systems at universities. In fact, at the last Internet 2 meeting in Washington, D.C., that was about 3 or 4 weeks ago, I had a joint presentation with a gentleman called John Chapman. He is from the Georgetown University, and we presented about the deployment of a big room, a full room with a lot of video screens and a lot of microphones embedded in the walls that they have deployed between their office in Washington, D.C. and their remote office in Qatar in the Middle East. So obviously they're saving a lot of money and a lot of travel by using this technology. And it was a very well-received presentation. And in fact, I was invited to present the same thing in very close to where you are from in Santiago de Compostela in 2 weeks at the EUNIS conference. I'll have the exact same presentation. So what I heard in Bruges was that university planned to deploy a desktop client. They're concerned about the cost. They're concerned about the licensing. They're concerned about the bandwidth on the local network. The bandwidth concern is not very popular here in this community. TNC is always happy to have like bandwidth-hungry applications, but once you hit the access network and go on campus, bandwidth does become a problem. So we're very proud to be in the bandwidth reduction business. Polycom is actually reducing bandwidth. We're very good at compressing video, like taking a 1.5 gigabit video high definition file and compressing it to something like 1.5 megabit per second. And we're very proud that we're able to do that because it does work in many environments. The complexity of the network has increased, and it will continue to increase as more and more people start using video. So really the issue is defining the term management and identifying which components have to be managed and how. And when I joined Polycom 3 years ago, I spent about 6 months trying to figure out what management means for video networks. So I'm now, 3 years later, I think I'm a little smarter and I can pretty much summarize in this presentation what I know about video management. I also have another presentation at 3 o'clock where I'll talk about video from a scalability perspective. So I'll be talking about how to create a scalable video network and how to remove the bottlenecks, how to remove the places where video doesn't flow very well. And it's not the network, by the way. It is the video conferencing servers. It's the gateways that create the problem. The network, like Gen 2 or Internet 2, are not the problem in this case. So this is the agenda for my talk here, and I'm happy that I have additional 15 minutes. Hopefully we can use that time. First, I wanted to spend a couple of, show you a slide or two from our explaining our vision for video. And it is very straightforward vision. Polycom has been in this business for a long time. We started with audio products. And then about 10 years ago, we started acquiring companies in the video space. Actually, 10 years ago, we believed that video will happen. It didn't happen quite. So now 10 years later, we are actually persuaded that it is actually happening. So that is, the vision is explained in a couple of brief slides. And then I wanted to give you the basics of high definition video and audio because I realized that sometimes, I experience the same thing. You go to an event and people talk about things and they assume that you know all of that. And then you realize that actually a lot of the fundamental knowledge is not there. So I just wanted to invite a colleague of mine to tell you over video a couple of, the basics of high definition voice and video and how they actually help you achieve certain applications or implement certain functionality. Then with regards to management, I'll talk about device and soft client management, which is something that some of you are familiar with. But there's also something called conferencing management. Some of the administrators, if there are any administrators of conference bridges in the room, they probably know what I'm talking about. But then there's something new and very unique to our product line is the conference resource management flexibility, and I wanted to touch on that as well. Then I'll talk about management tools, show you a couple of screenshots and a couple of video clips, and finish the presentation with a reference architecture that is a little more complicated, so if you feel tired, you can skip the last slide. Our vision for video, for visual communication in general, is very straightforward. We think that it's gonna change our life tremendously. Video is gonna be available everywhere. It's gonna be available to any audience. It's not gonna be limited by time, by place, or by device. We're actually seeing right now, most of our efforts right now are making real-time video as high quality as possible, but also we have a lot of new developments in the area of streaming and archiving because we see a lot of growth in this area, and we see a lot of in a lot of countries, in a lot of places, you cannot actually get real-time video. So you have to step back and say, well, if I cannot do high-definition video or even standard definition video, how do I deliver any kind of video experience to this audience? And streaming is a good way of doing it. And then you can fix the interactivity by using a chat session, for example, in parallel. So with regards to devices, for example, I'll be talking about room systems and personal systems and soft clients running on PCs. These are some of the options for doing video. The summary of our vision, and we call it VC2, like video conferencing 2, the next level of video conferencing, is actually that all of the blue stuff that you see here, or everything that is on the right side, I cannot cover all of that in one presentation, so I will focus on the high definition component here because I think it's fundamental to everything we do, on the IT integration and the management aspects. In the subsequent presentation at 3 o'clock, I'll be looking at the scale, the open standard-based component, and this here, the room, desktop, and mobile. So I will try to cover the whole thing with the exception of the user interface. I'm not a user interface expert, and I don't feel qualified to talk about it. This is a slide that most of you are probably going to like because it has megabits per second. So that's very important. So as I mentioned, we're very proud that we can actually compress video. And you see, there was a presentation yesterday about a technology called DVTS or DTVS. DVTS? Yes. That's uncompressed video. And now, uncompressed video works fine to a certain extent, but even if you do standard definition, you end up with 40 megabits per second stream. And if you have a direct connection to the Internet 2 or to the Gen 2, you're fine with that. But if you are, like me, connected to a LAN going through an access network and then connecting to a high-speed network, then you have a problem. So what we do with standard definition video, we actually compress it down to something about 512 kilobit per second. In fact, we can do standard definition down to 384 kilobit per second. We're just reducing the frame rate. And in some applications, when you have a talking head kind of application, that's perfect. If you have more movement in the image, you may want to have 512 or even 768 kilobit per second so that you can do a real standard definition experience. High definition usually results in 1.5 gigabit per second uncompressed video. We take it down to something like 1.5. We're in the range of 1 to 6, and depending on how much bandwidth you have, you can get the minimum quality or you can go to the maximum. So if you have a personal telepresence system with a relatively small screen, you can start doing high definition at 1.1 megabit per second. The big telepresence systems, they have big screens. We transmit more data to make the experience better. We usually work at 5 to 6 megabit per second per screen. So the largest system we have has 4 screens, 4 large screens. If you multiply it by 6 megabit per second, or actually they work at 5 megabit per second, you end up with 20 megabit per second, and that's the maximum you can get from one single video location. The problem starts when you have many of them, and that's what is happening today. When you have 10,000 people using 1 megabit per second, you end up with the gigabits per second that Paul was talking about. So that is really the problem. The latest technology, and I'll try to make this presentation also a little about technology updates so that you know where we stand today and where we're going. Today, most of the systems that ship, or actually all the systems that ship with this quality, the high definition quality at 720p. The latest products that just started shipping are running at 1080p quality. So that's pretty much where the industry is. The bandwidth is a little higher for that. It's about, I would say, 2 times, maybe 3 times higher than for 720p. But it is all can be adjusted by working with the frame rate, with the resolution, and the bit rate. These are the 3 parameters that you have to adjust to get the optimum experience. And in fact, there's no proof, there's no scientific proof that this quality is better than this quality. In fact, I'll give you some examples where the 720p quality run at 60 frames per second is much better experience than 1080p run at 30 frames per second. So it is not just the resolution, it's the combination of different things. This is where I summarized what we use the different high definition formats for. This one is for regular meetings. This one is for meetings where you have a lot of motion. Then the 60 stands for 60 frames per second. And the 1080p is really very useful when you have high-end medical applications, when you do manufacturing applications, when you have people look at the same sample or the same chipset under the microscope in 2 different locations. That's where 1080p is actually very important because you can distinguish small differences and small problems in the picture. It's not that important when I'm talking to you over video. And here I would like to invite a colleague of mine who can provide a couple of examples how high definition video is used. Now I just need to find it. Is it here? Nope. It's not here. Here, maybe this is the one. The problem is that my Spanish is not so good. Where do I select? Click play and it will start because we already played it? Okay. Yeah, very sensitive this. Okay. Okay, here we go. So just enjoy the video. It's about 5 minutes long. And there's audio to it. Can we hear the audio?
Fundamentally changing business communications. Whether in an office or the field, on a webcam or immersive suite, video is increasing communication efficiency and reducing the cost of doing business for companies around the world. Video's popularity, however, has resulted in a host of terms, acronyms, and technologies that can complicate finding the right solution for your organization. What do you need to assess to make the right choice? First, review your applications. Will video be used for face-to-face interactions, content sharing, high motion graphics, or more? What resolutions and frame rates are needed to ensure optimal experiences? How much bandwidth do you need? What about display sizes and types? And can you ensure the choices you make today will last into the future? Let's take a look at these technical variables and consider how they influence one another in different applications. The first factors most people consider with video are resolutions and frame rates. Right now, you're seeing me in 1080p resolution. 1080 represents the lines of vertical resolution, while the letter P stands for progressive scan, in which all of the lines of each frame appear in sequence. You may also see resolutions like 1080i. The I stands for interlaced, and generally in the world of video, progressive scan is preferred because interlacing causes details to twitter and blur at the cost of image clarity. Now let's compare the impact of resolution and frame rate on an actual video interaction. Lisa and Larry are in a traditional video conference that uses CIF resolution and about 384 kilobits of bandwidth. Now let's see Lisa in standard definition, or SD, which is about 4 times the resolution of CIF and requires about 768K of bandwidth. Notice the level of detail and clarity Lisa has over Larry. Now let's move Larry to 720p, also known as high definition or HD. 720p at 30 frames per second uses about 1 megabyte of bandwidth and is a primary driver behind today's widespread video adoption. In this interaction, Larry's gestures and expressions become immediately more impactful. Everything we've seen up to now has been shown at 30 frames per second, but now let's take Lisa to 720p and also double the rate to 60 frames per second. This mode uses about 1.5 meg of bandwidth and is the equivalent of high-definition broadcast TV. Notice that even at the same resolution, because Lisa is being shown at twice the frame rate, her motions are much smoother. Now let's move Larry up to 1080p at 30 frames per second, which uses about 4 megs of bandwidth. So as you can see, significantly increasing the traffic on your network does not necessarily translate into better image quality. Note, Lisa will appear in better quality as her frame rate remains at 60. This underscores the importance of display size in selecting the appropriate resolution. While increasing frame rate has the same impact on any size screen, the impact of resolution declines in proportion with the display size. For example, PDA or cell phone displays support low resolutions but look great because of their small size. As a rule of thumb, the human eye can discern 1080p only when the display size is equal to or greater than 70 inches, and the viewer is sitting about 10 feet from the display. Not all video applications today involve face-to-face interaction. Now that Larry and Lisa appear to have made up, let's take a quick look at some applications illustrating the relative importance of resolution and frame rate. In this live musical performance, where motion smoothness and the ability to discern fine motor movements take priority, optimal viewing occurs at 720p resolution and 60 frames per second. Another example of where motion smoothness takes precedence over maximum resolution is in this clip, where a doctor is instructing a remote group of students in a new medical procedure using captured video as part of his lesson. In some cases, though, clarity and fine detail matter more than motion. These examples from healthcare highlight the importance of maximum 1080p resolution. It's essential for the remote physician to see fine detail, such as an enlarged blood vessel or changes to the cornea. And in this example, the remote consulting physician sees the diagnostic image in 1080p high definition, enabling an accurate diagnosis of a patient hundreds of miles away. The importance of detail also extends into commercial applications. In these two examples, 1080p enables remote quality inspection of two very different products: a printed circuit board intended for use in consumer electronics, and a garment being manufactured for the retail market. In the world of video, clearly, one size does not fit all. Balancing quality with cost-effectiveness by choosing the right combination of frame rate, resolution, and bandwidth for your environments and requirements is critical. Whether you're video enabling desktops, conference rooms, lecture halls, or immersive suites, we hope this video helps you make a more educated decision. For more information, we welcome you to contact your Polycom representative. Thank you for watching.
Okay. Well, that hopefully made the presentation a little more interactive. I hope you enjoyed the video. And I will go back to my presentation slides. so difficult with this mouse. Here we go. Here we go. So when we talk about video, usually people focus on the visual component of it. One thing that we usually forget is that there's always an audio component to video. And that's where a lot of work is being done. And it's not very visible because audio is not as easy to demonstrate as video is. People react immediately on images, while audio it becomes very important when you start using video technology. In fact, what I found out in my conversations with people who use high definition video is that their expectation towards audio grows as well. So if you offer a system or solution that has high definition video, but the traditional public switch telephone network audio quality, people are unhappy because it really destroys the experience. And after a short while, the image quality does not matter anymore because they're still having problem hearing the remote site. And still we're getting a lot of the information or most of the information in a business meeting or an educational setting from the audio. So that's why we are spending a lot of time working on improving audio technologies. And what you see here in the upper right corner is really where the action is. These are the new technologies that actually enable systems like telepresence or applications like telepresence. The music applications that you saw, there was a portion of the video clip where they showed how the Manhattan School of Music is using our technology to connect multiple campuses and do remote presentations and remote music performances and instructions. That is enabled by this kind of technologies here. It is impossible to do with this. This technology right now, well, this is the initial voice over IP technology that became available about 10 years ago. And it was all about compressing down to something like 7, 8, 10 kilobit per second. Now this problem is gone. Now the focus is in this area. Most of the voice over IP telephones today work in this range, and they usually support something like 32 kilobit per second voice. So these are all speeds that are very funny for people who work for TNC, but in many environments it is important. For example, in mobile networks, there is a bottleneck for bandwidth. This is actually what is most important to us because it really provides not only the ability to communicate and talk, but also to transmit music and natural noises. And that's the next frontier of visual communication. How do we make these video applications applicable to other segments of the market, to other user groups? Beyond a basic video call. And you saw some examples in the video clip where video is being used to develop product jointly and look at samples, where video is used for remote medical application, for education of medical students, etc. So these are really the applications where we see a lot of growth, and it's all enabled by high definition video and high definition audio. My intention was to play a couple of audio files and just to give the impression how good the new technology, the new audio technology is. But I think I'll skip that. If somebody is really interested in that, you can stop by after the presentation and I can play you a couple of audio files. The best result is really when you're listening to that on a headset. It's fairly difficult to demonstrate audio in any kind of open environment, and it's especially difficult to do it in a trade show or a conference environment when you have a lot of background noise. So that's why video is always a great demo. Audio is always a problem. In fact, if you have seen any interoperability tests, and there are a lot of attempts to connect different systems for video calls, you will confirm my experience. My experience is that video always works, and there's a reason for that, because everybody uses H.264. So everybody connects, and there's no problem with the video. Everybody has problem with audio. And the reason is that there are so many different audio codecs and audio standards out there, and some of them on this slide here, that when you connect, the video is perfect, the audio does not work. We had this experience twice at the last Internet 2 meeting where the video was perfect. We had high definition video, but the audio did not work. And hopefully the audio industry also converges around one single standard, and we have actually a candidate. We support a candidate in this space. That's the G719 codec that was developed jointly between Ericsson and Polycom. And that's the one that we actually think fulfills all of the requirements for high quality audio for music applications and conversations, both of them. Now I have some time to talk about management. And first, about a definition of management. Management is really the ability to control devices and soft clients, because soft clients are not considered devices, as well as conference servers, recording servers, streaming servers, etc., control them remotely without having a technician to go on site and do the configuration locally to the device. And it's really about the business, return on investment for deploying video technology. In the moment where you start sending technicians and to the different sites to fix the problem with the equipment, you're incurring a very high cost, and your whole business case for deploying video may go downhill because of that. So really the management is a very important component when you have a distributed network that goes across campuses, across continents. And it all starts with the first deployment of any kind of video device. That's where you do the first startup, the first provisioning of the device, and the first software upgrade. And then throughout the life of the device, throughout the operation span of the device, you have multiple provisioning processes, and you have to change the software a couple of times. You're monitoring the device constantly, and scheduling is something that is very specific to video. You're using scheduling software to plan ahead for using video equipment. Very important when you're using rooms for video. Licensing is very important. It starts from the first deployment and it goes across the whole life of the device or soft client. And at the end, the removal of the device happens in two ways. You either disconnect the hardware box, or if it's a soft client, you basically deinstall it, and then it's gone. So really, management is all of that. Everything on this slide is considered management. With regards to provisioning, this is a very basic slide that explains how provisioning works, but basically the idea is that when you get the new equipment and you install it, you plug it into the IP network, you have to get some information to get it up and running. And this information comes from a management application that runs somewhere in the network. There are several approaches how to do it, and I will basically give you the concept. I'm not going to give you any details or try to avoid talking about how we do it. There are several approaches how to do provisioning. The best one is when the device itself contacts the server and retrieves the information. That works very well when you have firewalls. That works very well when you have multiple applications running on the same server. Because if the alternative would be that the server goes and scans the network and finds the devices, that's very resource-intensive operation. And it's actually considered a security threat, because a lot of the security software will identify that as a hacker attack and will basically disable the ports to the management application if you start scanning the network. It also is not going to work if you have IPv6 deployment, because the address range is so huge that scanning will take you a lifetime before you find anything in the network. So really it is about the video endpoint or the soft client contacting the management application. That's, by the way, the old-fashioned way of downloading the phone book, the video telephone book or the video book, contact address book to the video endpoint. The new method is really using XML running over HTTPS. This is an example of a provisioning file. I just took one that I had from one of our systems. You see that there's configuration of XMPP, there's configuration for H323, and if you go below, I didn't put the whole file, there's a zip configuration, et cetera, et cetera. So it is very easy to read and manipulate. In the past, we were using text-based files, but XML is much better because you can parse it. You parse it on the endpoint, and if the endpoint understands the command, it executes it and changes the parameter. If it doesn't, basically it logs an error and keeps going. With text files, we always had the problem that an error will basically take the endpoint down, and it's not very flexible. So XML is much more flexible. You can change it dynamically, and if something happens and the endpoint does not understand the command, it just keeps going through the file. Software upgrades are very important because we have different software loads for the different models, and they're all running on different operating systems. And also, you don't want to have all of your users on the same software load. If you have a new version of the software, you don't roll it out to the boss. It doesn't matter if it's an enterprise or a university. You really want to keep that in the IT department for a while, and when it gets tested and established, then you can roll it out to wider audiences. So usually you keep a couple of software versions, like a new one, a tested one, and a very tested one on your server, and deploy it based on the audience or the user profile. The initial configuration usually happens through DHCP. Manual configuration is not recommended. Some people are trying to put IP addresses manually, but that's not a good idea because it doesn't scale. And DHCP is the best way to get this initial configuration. The most important thing is really to get beyond the IP address and IP mask, etc. The most important thing is to get some server information. And the most efficient way to get server information is using the DNS SRV to find the management server. We have tried everything from using DHCP to do that, or manually doing that, or asking the user to do that. None of that works. It's really not a way of doing it. The only way that really works is DNS SRV. Basically, you send a request, or the video endpoint automatically sends a request saying, I'm looking for a management application in the network, and that's my domain, the abc.edu in this case. And then the DNS servers send back a list of management servers and assigns priorities. And in this particular example, the first priority is the management server number 3. If the video endpoint behaves as expected, it will connect to this management server and retrieve information from it. If something happens and this server fails, then the video endpoint will go and pick the priority 2 and connect to the management server 1 in this case, which is up here. So this is very good mechanism to avoid single point of failure and make sure that management always works. Once the server is found, the video endpoint sets up a channel. The most modern way of doing it, and that's the latest generation of equipment, is for XML running over HTTPS. And that's basically the handshake. It's using the TLS, the transport layer security, to set up a tunnel, and then in the tunnel the endpoint sends a request and gets the provisioning data in the XML format. This is a very secure mechanism. All of the other mechanisms that were used in the past, going through Telnet, going through FTP, going through TFTP, they all had problems with security. So this is the only secure way to do it these days. The most important servers that you need to configure are the gatekeeper or the SIP server if you're using SIP for signaling. The directory server is very important because you want to make sure that you have a contact information and know who are the people in the network and where to find them. And the presence server became very important in the last couple of years. Presence is now coming through the unified communication path. And we're working with companies like Microsoft and IBM to integrate with their presence servers. And it's very useful. Using presence is very useful, especially for soft clients, because you can really start a chat session with somebody and find out if they're available for a video call, and then you click to connect over video. It's actually not considered polite. And in our company, we're using video all the time. It's not considered polite to contact somebody directly, to call somebody directly over video. It's actually much more intrusive than calling somebody over the phone, because you are actually, if the auto answer function is activated in the video endpoint, you are automatically connected and you can peek into somebody's room. And they may be not ready to talk to you at all. So it's really a good manner or a matter of etiquette to first send a message, agree on a video call, and then connect. Another interesting function that you have to support in a management application is the ability to configure groups and sites. And the idea here is really that every site has specific provisioning or a specific configuration that is different from everybody else. You may have some local gateways, a local directory server, a local outbound proxy for outgoing calls. This is specific to a particular site. But then you can group the devices based on a model or what kind of device it is. Some things make sense for a room system. For a room system, you may want to configure a home display, some kind of a home display that is there that is displayed when the system is idle. Or that doesn't make sense for a soft client, for example. So for soft clients, you can configure other things. Like instant messaging, for example, makes perfect sense for soft client. It doesn't make any sense for a room conferencing system. Cascaded software deployment is recommended because, and it works like this. You basically, instead of having all of the video endpoints connect the management server at the same time, there's a time offset. So you basically, the first video endpoint connects, and then the second and the third, and et cetera. And that is very useful when you have a power outage. When you have a power outage, you may have 1,000 clients or 10,000 clients down for a couple of seconds or a couple of minutes. Then power comes back. Everybody goes to the management server, and the management server crashes. So you don't want to have that. So you really want to have this time offset so that everybody can get configuration information. Monitoring is usually done through SNMP alarms, mostly SNMP version 2 today. Version 3 is better from a security perspective. Soft clients usually do not use SNMP for this purpose because it's really designed for hardware components. Soft clients, usually what we do is basically at the end of the call, we get a file, we create a file that has all of the statistics of the call and we send it to the management server. And the management application can actually decide whether to generate an SNMP alert to a third-party management application, but we're not sending SNMP directly from a soft client to the management application. Licensing is a challenge because in the past you would need to go to every single device and put a license in it. And today what we're doing is actually we're using a client access license, which is one file that you put in the management server, and the management server does the counting, counts how many clients are in the network, and that allows you actually to remove one video endpoint and put another one, to remove one or to deinstall a client, a soft client, and install it on another PC. You have, or Mac, you have the same number of licenses. That was a problem in the past because Mac licenses are usually connected to MAC addresses, and when a device is broken, you have to go manually and change the association between the MAC address and the license, and that took so much time, it was just not very productive. Client access license solves that problem, and it works beautifully. And also it gives you, if the manager who is looking at the management application dashboard, if they see that they're running out of licenses, they can immediately go request additional licenses and upgrade, and it's just one file that they get. They don't get hundreds of files for all of the elements in the network. And by the way, we're using the exact same management application for all sorts of systems, telepresence system, personal video systems like this one here, room conferencing systems or soft client. They're all using the exact same licensing, provisioning, software upgrade, et cetera, mechanisms, and that makes it really work beautifully in a diverse environment. Device control is another interesting function that allows you to tell a device or tell a video endpoint to make a call to another video endpoint. And it's something that can be done in multiple ways. It is useful when you have a scheduling application, for example, planning a call between you and me tomorrow at 2 o'clock. You don't have a bridge to do the dial out, so instead of using the bridge, you basically send one of these messages and my endpoint calls your endpoint. There are several ways of doing that as well. And conference management is something that happens in the conference server itself. I described it here because it's different from device management or soft client management. Conference management is really about how you set up a conference, how you manage the conference, and how you terminate the conference. So for those of you who have experience with video conferencing servers, there are a set of commands that you can do. And depending on what role you have different access. Participants have a very limited number of functions that they can do. Chairpersons usually have a full control of the conference, and the administrator has even more control because they can go and peek into every single conference that is running on the server. And since a lot of the video calls today are still scheduled, especially in education, there's a need for a scheduling tool. And this is a screenshot from a scheduling tool that we provide. It's part of our converged management application. It's just one of the functions in it. And it basically allows you to put time, drag a couple of people into the tool and set up the call. There was a big discussion over the last couple of years, and for those of you who are involved in video conferencing, you probably heard about it. The whole concept of a port is a port. There was a line of thinking over the last 3 years that that's a better way of doing video. And it's really two philosophies related to how you do conferencing. One is saying that you have to have a set number of ports. So you're buying a bridge or you're buying a conference server, and it has, let's say, 60 standard definition ports, or it has 40 high definition ports. And it makes life easy for the customer. I do not agree with that. I think that it doesn't make my life easy if I can only use this component for one particular type of call. So that's why I prefer, and we actually prefer the dynamic way of assigning resources. So the flexible resource capacity is much better. We ended up supporting both of them. So once you get like a Polycom bridge, you basically can set it to be one or the other. And this is my last slide that I warned you about. It's our reference architecture that basically explains what components come in the data center and what components are placed in the different parts of the network. The example is for enterprise, can equally be applied to education as well. I just didn't have time to redraw the picture. One final slide. The hot new area in management is how do you manage multi-screen systems when you have multiple codecs? They have to behave as one thing, but you have 2, 3, or 4 codecs or video endpoints connected into one. And this is for the telepresence system that I have here. This example is for a 2-screen system. This is my contact information. There is a paper about this particular subject. It's a little different from the presentation, but you're welcome to download it from the blog site. You can just type video networker in Google and it comes up first, so you'll find it very quickly. And feel free to send me an email if you want. Thank you so much.
So we are in the schedule, but I will allow 1 or 2 questions. If there are no questions now, you can find Stefan in the lunchtime and also during the rest of this conference, so you can speak with him. So let's thank again the 2 speakers of this session. Thank you very much for your interesting presentations. And before we leave the room, I will call your attention again for the demonstrations during the lunch break at the exhibition area, and also for the poster presentations during the afternoon coffee break, all in the exhibition area. So please don't forget to register your comments on the evaluation form and have a good lunch. Thank you.